This lecture will be on asynchronous programming using callbacks. Asynchronous programming is one of the key recurring topics of this course, and it is intertwined with many other topics, not just in the programming aspect, but also in the networking theory components, especially when we get to the transport and the application layer. The reason why we use asynchronous programming is because when we're working with networks, we may have tasks that take a very long time due to network latency. And if we have dropped connections, those tasks may never complete. So it doesn't fit our traditional procedural model very well, where we have two tasks, let's say task A and task B. And if task A needs to use the network, but that message gets dropped or lost, then because task A is preventing task B from even starting, this program will sort of starve because it's waiting for this task to complete. Let's first look at a quick demo. Okay, so over here we have a loop that just busy waits, and then when it's finished, it'll print a message console.log finished. So I'm going to copy this. I'm going to navigate to the course webpage, and I'm going to open up the inspector by pressing Control-Shift-I, and I'm going to navigate to the console tab. So when I run this code, I'm going to paste it in, I'll push enter to run it. It'll run for roughly 10 seconds. And afterwards, it'll print out the message finished. And because this loop over here is what we call blocking, we won't be able to interact with the page until the finished message prints. Okay, so if I try to do something like run this code and then highlight some text or right click, those will not occur until the finished message prints, and then they'll all sort of happen at once. Okay, so let me sort of quickly show that. So I'm trying to highlight some text, it doesn't work. I'm trying to highlight some other text, I'm going to right click two or three times. And you can see that when the sort of timer finished, all the highlights happened in quick succession. Okay, so in contrast, we'll compare this to the Set Timeout function, which is used to create a non-blocking delay. Okay. And if I run this and I select some text, if I right click, and if I click a button, none of these are prevented. And after the 10 seconds pass, it prints out a message finished. Okay, so we can see that on the front end, when we're interacting with user applications, running our code asynchronously can be beneficial. Okay, but even on the server side, it is also useful when we have tasks like reading a file or making a network request that may take a long time. Before we go into demos, I'm going to discuss very briefly the libuv library. So libuv is a C library that provides support for asynchronous IO-based operations using the event loop. The architecture underneath of it has two key parts, the event queue and the event loop. Okay, how these work is when our application makes a asynchronous request using the Node.js API, JavaScript will send libuv a request to interact with that API. Okay, so for instance, if we're trying to make a network request, okay, our application will tell our engine that we want to make a DNS request to, let's say, this website. And libuv will add that task, okay, to its task queue. And that's all it does. Okay, so it doesn't do that task right away. Okay, and once that's done, our application will move on to the next step. Okay, so we can see that it doesn't sort of, even though this task may take a long time because it has to go off to the network, our application will move on to the next task right away. Okay, so from the task queue, we have a worker thread pool, which is going to depend on how many sort of CPUs and cores that your computer has. It will, each of these will pull tasks from the task queue. Okay, so as the tasks come in, they'll get pulled off and worked on. For certain applications like fs.readfile or fs.write file, we don't actually need CPUs. We need to access disk, and so we have a separate mechanism, IO polling, for disk-based operations. Okay. Now, regardless of what happens, when these tasks finish, whenever we perform an action that is asynchronous, we have to supply it a callback. It's essentially a function that tells you what should be done when this task completes. All asynchronous functions not only have a task that they want to complete, but they also contain a callback that executes when that task is completed. Okay, it must have that second part as well. And that callback is going to be placed on the event queue. Okay, so it's going to be pushed into the event queue. The event queue is very important because V8 is single-threaded, so it can only accomplish one thing at a time. And so we have this event loop, and what the event loop is going to do is it's going to periodically check V8 stack to see if there's anything still on there. Okay, then we still have some code on there. It's going to wait a bit, and then it's going to check again. Okay, and then finally, eventually, this V8 stack is going to be empty. Okay, and when it's empty, it's going to move the first task from the event queue onto V8 stack, and the program will continue execution. This is how we can do multiple tasks even though V8 is single-threaded. So let's look at the second application, since the first one is just the lab where we played with the browser. Okay, so over here we are reading a file, file 01. File 01 just has the text hello world inside of it. And over here we have our callback. This highlighted piece of code is our callback. In the second example, I rewrite it using a arrow function notation. Okay, and in this third one, I rewrite it using a named function. Okay, so over here, fs.read file, we have this function do after reading. This is my preferred format, but all three of these are equivalent. This one uses a anonymous function, a function with no name. This one uses an arrow function, which is also anonymous in there. And this last one is a named function. Okay, so what's going to happen is over here we're going to read a file, input / file01.txt. We're going to read it as if it was UTF-8 texts. This is called the encoding format. And finally, when it's finished reading, we're going to run a function do after reading. Okay, and this is because when we're reading a file, we don't really know how long it's going to take. Okay. So depending on the file, it might finish in a couple of milliseconds, or maybe it might take a minute or so if it's a very large multi-terabyte file. Because we're only going out to disk, we're we're only telling the disk that we're only telling the disk to perform some action, and we're not doing anything with the CPU, it doesn't seem right to sort of prevent the CPU from doing something else. Okay. Okay, so before we actually run this, I think this one we can run in the VS Code debugger without any issues. Okay, but all right, so it prints out the length of the file, which is 11 characters. But there seems to be a bug in Visual Studio 1.49, which is the latest version currently, where if we do DNS requests, the terminal doesn't match. I can quickly show this, I think, with example 6. Okay, so over here, we can look at the console messages. You can see we have console.log prints immediately, failed to resolve, print immediately, failed to resolve. And this prints out the results, but there should be some IP address and some records. And if we run this over here, you're going to see, well, this one actually worked. But if we're running it again, right, sometimes it prints out canceled, which is definitely a bug. And we can avoid this bug if we don't run it using the VS Code interpreter. So I'm going to run our programs directly from Node itself, and I'll show you how to do this. This is also something that's important to be able to do if you're not using VS Code. Okay, so we'll start with in fact, we'll start with this one. Okay, so to run our code from within the Node application and not within VS Code, you're going to start up a terminal and navigate to the current location. If you're on Windows, this can be done very easily by just holding Shift and then right-clicking. You'll see a new window called Open PowerShell here. And if you click that, that will open a terminal to this location where we can execute our programs. Once you've got a terminal open and navigated to the correct location, you can run your programs by typing in node, followed by space, and then followed by the file name. And another quick shortcut that you can do is instead of typing the file name, you can just hit, after you do node in the space, you can hit tab, and it'll cycle through each of the files available to it. Okay, so in my case, I want to run the first program, which will print out finish reading file 11. We can do the second one, and the third one. Okay, so these three are equivalent. Let's move on to the next piece of code. So the next piece of code uses the DNS library. Okay, so the DNS stands for domain name server, domain name system, and it's a internet service that converts human readable domains like facebook.com or cs.qc.cuny.edu into machine readable IP addresses. Okay, so typically machines don't really know what this means, but there's a lookup service on the internet that converts these domains into IP addresses. Okay, and if you think about it, when you register a new website, how does that information sort of get populated to all the other computers in the world? And the DNS service provides that. Okay, so to use the DNS package, to use the DNS library, we need to require DNS. Okay, so this will import all the methods that we need. So in this case, the domain that we want to resolve is vns.cs.qc.cuny.edu. And so we're going to call the function dns.resolve on our domain. And because this is accessing the internet, it's going to take some time. So it's done asynchronously. Okay, so this specific function is designated as asynchronous. And we need to supply it. Again, when you're doing an asynchronous function, typically you have some task that you want to do. In this case, we want to resolve this domain. And then you need to also supply it a secondary callback. What do you want to do when it's finished resolving that domain? Okay. And in this case, we are executing after resolution, which will do one of two things. Typically, when you have a callback function, it's going to supply at least two arguments, and these arguments are defined in the specifications. And we navigate to dns.resolve. Okay, so the callback over here returns back two arguments, error and records. So error only has a value if there was an error in the resolution process. For instance, if you unplug your network cable or you turn off your Wi-Fi, then it won't be able to resolve. And if there's no error, then records will have some value, which means that it was able to resolve. Records is going to be the array of IP addresses that was returned from the DNS requests. Okay, so let's run this. Okay, so we can see that VNS is IP address, and it returns back an array with 149.4.99.190. So it's an array because in certain cases you can have multiple IP addresses that get returned back. I think cat.com resolves to 2. Okay, right, so cat.com resolves to 2. So sometimes you can have multiple IP addresses if they're doing something like load balancing. Now these are done asynchronously, and I want to very quickly just print right away. Okay, so one of the key things you have to know is that this function, dns.resolve, is not blocking. Okay, so it's an asynchronous function, and when I call it, the function underneath of it, this console.log prints right away. It will print without waiting for the domain to come back. Okay, so if I run this over here, it will print right away. Okay, and the important thing that a lot of people get stuck up with is they think that this might have a race condition, that sometimes it might resolve first, and that is not the case. This always prints right away. Okay, so no matter what, even if let's say that after resolution finished instantaneously, even in that scenario, this statement prints first, even if it takes no time at all. Okay, and to understand that better, we're going to quickly go back to the architecture of libuv. Okay, and so when we call Dns.Resolve, this is a asynchronous call. Okay, so that goes to the task queue. Okay, and so it goes in the task queue. And what happens next is V8 should execute console.log always prints right away. But let's give it the benefit of the doubt that it doesn't have the CPU right now, and that the worker thread pool has taken decided to work on Dns.Resolve first. Okay, and so let's say that this finishes again instantaneously. When it finishes instantaneously, this results the callback after resolution. It gets placed on the event queue. Okay, it doesn't get called. The function gets put into the event queue. Okay, so this is now inside the event queue, and the event loop will continuously monitor V8 to see if there's any other tasks that if there's any other tasks on its stack. And V8 does still have a task. It has this task that we've sort of pushed off. We're trying to delay from executing. So as long as this task is still on V8 stack, it cannot move this function onto the stack. So you can sort of see that this is the reason why this will always print before this function after resolution fires, because it's literally blocking it, because the event loop will only move this function into V8 stack when this one has cleared. Okay, so hopefully that sort of illustrates it a little bit better. Let's look at DNS2. DNS2 is the exact same. The only difference is that it's showing that function declarations can be anywhere. So over here, we just moved the function declaration to the very, very top, even before the library definitions, and this should work as well. Okay, so it's exactly the same. Let's move on to the next demo. Okay, so over here we have multiple tasks. So completing tasks synchronously, we want to complete one task after another. In procedural style code, we can just sort of stack the tasks, put one right after the other. We're going to see that this doesn't work. Over here we have, again, we're using our DNS library. We have the domain that we want to resolve, and we have some variable data. Okay, so over here we're trying to resolve the domain, and then after we finish, we're going to call it after resolution. And then what we would think would happen is, well, if we put next task over here, and then all this is going to do is it's going to have the data, and it's going to call this function to print it. And what we're going to actually get back is that this variable date input or data over here is undefined. Okay. Okay, so this is undefined. And again, we'll go back to the architecture to sort of explain what's happening. Okay. So first, this is the asynchronous task that gets called to Dns.Resolve. And so again, we're going to assume that this asynchronous task takes priority. We're going to sort of give it the benefit of the doubt that it runs as fast as possible. And so it goes, when we call it, it goes into the task queue. The worker thread, one of the worker threads pulls it out and makes the network request to try to resolve it. It finishes immediately because we are right next to the DNS server. Okay, and it gives us back an answer almost instantaneously. And when it does, okay, so after we have that, then we have this callback function, okay, that we've added to it. And it doesn't, again, it's important to know that when we get a response back, it doesn't call it. It doesn't call this function. All it does is it takes this function and moves it into the event queue. Okay, it moves it into the event queue. And then the event loop will periodically check V8 to see if the stack is empty. And the stack is not empty because I still have to do all of this. Okay, all of this is not done yet. Okay, so I can't move this function into V8 stack. Okay, so even in the sort of best scenario where we finish all of this immediately, we still can't run this function. Okay, so we're forced to run this function. We're forced to run next task. Okay, and what does this do? It takes in a variable data, which we have over here. What is data currently? Well, because I haven't executed this, data is just undefined. And then when I print it, it's going to print undefined. It's always going to print undefined. There's no race condition here, okay? Even in the very best scenario, it will always print out undefined. Okay, so how do we get this synchronous behavior? We can look at the next demo. Okay, so to get the synchronous behavior, you place the secondary task that you want to occur inside of the callback. Okay, so in this case, instead of having next task down here, we have next task called over here. We have next task called from within the after resolution function. In fact, this should not have a semicolon, so I can fix that. Okay, and in fact, I don't even need this. When Dns Resolve executes, again, we're making a call to libv for Dns Resolve. It's going to add that task to the task queue. And again, we're going to be very generous. We're going to say that that task executes and finishes immediately. The function after resolution gets added to our event queue. And V8 is going to finish the rest of its tasks. And the rest of the tasks is just to define this function next task, which in fact this was done much earlier because all functions are defined when the program makes its first pass. So in fact, this is the last statement that executes. So at that point, the stack is now empty. So because the stack is now empty, this function after resolution gets moved into V8 stack. And so what does this function do? Well, it's got a variable records. It checks to see if there's an error. If there's an error, then it'll print fail to resolve. Let's assume that there's no error. If there's no error, then it's going to say, it's going to assign records to data. And then it's going to call next task of data. Okay, and that's going to call this function over here. And then it's going to print out our variable data. Okay, so notice the difference in this case. Instead of having next task on the outside of the code, we move it into the callback function. And the callback function will trigger the next statement. Okay, so let's run this. Okay, and so this one prints out a IP address. Okay, so this next example uses two DNS requests back to back. First we'll resolve Venus, and then we'll resolve Mars. Again, this is where we start to get issues with the integrated debugger inside of VS Code, inside of the version 1.49. Hopefully they fix it soon. But it doesn't matter to us because we're running our program from within the command line. Okay, and so let's look through this program code. Okay, if I jump back up to the libv picture. So first we're importing our library DNS. We're declaring two variables, Venus and Mars. We have a address, an IP addresses array, And over here, this is our first function called Dns.Resolve. And notice that it's also the only one. Over here, there's a function definition. Over here, it's a function definition. So this will be the last statement of our program stack. Okay, so we're going to resolve Venus, and we're going to call it after Venus once finished. So DNS.resolve on venus.csxq.edu. Again, we're going to assume that we're very generous, that it's going to finish immediately. So it goes on task queue, goes into a worker thread pool. Worker thread pool performs the necessary networking applications, gets that data back. Once it gets the data back, again, that this function, okay, after Venus, gets added to the event queue. And our event loop is going to continuously check the V8 to see if there's anything left to do. As this was the last statement, V8 stack is now empty. It's going to move after Venus into V8 stack, where the application continues. We'll also assume that there's no error. In that case, the IP addresses gets added to the array records. And then we perform the next task. Okay. And in fact, this one's a bit interesting because even if there was an error for this one, we still perform the next task, which is what you want sometimes. Okay. You don't want the program to just completely sort of freeze or crash if there's an error. That is something that you can resolve and move on to the next one. Okay, so this performs another DNS request. Okay, so we can sort of see we have a bit of recursion over here. We have a DNS request that makes a DNS request. When it's finished, though, it calls the function after Mars. Okay, so again, from within inside of here, it's going to make another request to libuv. Libuv will add that task to its task queue. The worker thread pool will pull one out once it's available. And then once it's finished working on it, it will place the callback, after Mars in this case, into the event queue, where your event loop will again continuously monitor to see if there's anything new. It'll see that there's something new, and it'll move it into V8, assuming that V8 stack is finished, okay, which it was. So this was the last statement. This was the last statement for this function after Venus, so that got cleared out afterwards. And so what does this mean? So what does this mean for us? This means that this statement will, once this statement completes, and only after it completes, will this function trigger, which will also mean that because this one calls a Dns.Resolve and after Mars will always finish after Venus. Okay, so the order is we resolve Venus's domain, we run the callback after Venus, then we run the Dns Resolve for Mars, and then afterwards we run the callback for Mars. In this case, it also pushes the IP address to records, and then at the very end, it combines them using a comma space and runs the program. So let's run this. Okay, so you can see that no matter how many times we run it, it will always print out Venus's IP address before Mars. Okay, so this is what we call performing tasks synchronously, even though we are using a asynchronous API. So this style of programming has a special name. It's called continuation passing style, where the very last statement of the function that we're executing makes a asynchronous call. And that asynchronous call sort of passes the baton off to another function. The next example looks into how to make concurrent requests. So if we need to make, let's say, 2 requests at the same time, the first 3 lines define the Dns library and the 2 domains that we want to execute. And then we resolve the Venus domain. Afterwards, we print out a message. After we schedule this task, we print out a message, prints immediately 0, 1. Then we schedule another task to resolve Mars. And then we print a message, prints immediately 0, 2. Both of these tasks are added to the task queue, and a worker thread will grab them as it gets free. Okay, so even though Venus gets added to the task queue first, that doesn't mean that the worker thread pool will finish this first. Okay, it might take, it might be much easier to resolve Mars. Okay, and if we have, let's say, multiple cores and stuff, it can sort of do both of them at the same time. Now, because these two could take different times, for instance, let's imagine that one of these domains was google.com, something that is highly cached, then that might finish first. And so whatever one finishes first, that gets put onto the event queue, and the other one will get put onto the event queue as well. But we have no guarantee about order. Okay. Once V8's stack is cleared, it'll pull the first task out, so it'll execute it, and then it'll do the same for the other one. So in this case, we can sort of do these two tasks concurrently at roughly the same time. Okay, so let's run this. Okay, so it prints immediately 0, 1 and 0, 2. Okay. And again, this is because running this step only schedules the function. And in order for either one of these to move on to the call stack, everything on the existing call stack must have executed first, including both of these console.log messages. So this is the last message that happens before the first callback happens. Now in this case, the most likely you'll see the same thing when you're running yours, that Venus appears before Mars in this scenario. And I'm going to change the domain a bit. So I'm going to change this to red.cs.qc.id. I'll leave all the variables the same, just for time sufficiency. But over here, because I didn't visit Red recently, and I did visit Mars recently, most likely that this is cached somewhere along my path, you can see this time it resolves Mars first, even though the only thing I changed up here was the string name. So it's no guarantee what occurs first, but there are some factors that sort of help me, and that I assume that there's some caching going on. If there wasn't, so even this is not guaranteed to sort of print Mars first. I just got, I wouldn't say lucky, because I would say this was sort of engineered to give me the benefit of the doubt, because Mars was likely cached because I ran it like 1 second earlier when I did Venus and Mars. So when I compare Mars and Red, most likely Reds would be slower. This sort of proves that the order is not guaranteed. So after Venus and after Mars have roughly the same code inside of them. And so one of the things that you might consider doing is to try to generalize it into a single function. Let's call it after resolutions. And this is going to be harder than you think without using special constructs. And I'd definitely recommend that you try it first. You should pause this video and try to code it up yourselves, because you learn more about the problems that's going to arise by doing it yourself, and it makes you a better programmer. Okay, it's perfectly fine to get stuck and not know the solution, but you should definitely try it, because it gives you more intuition about how callbacks work. Most likely your first attempt at a solution would look something like this. We want a function after resolution that will sort of print out a domain, and then followed by the IP address. And the issue that we have at hand is that when we call Dns.Resolve and we pass in, let's say, Venus over here, the callback that we execute doesn't have any way for us to sort of generalize which domain that we were working with, whether it be Venus or Mars. Okay, so we want to have something like domain over here, but we don't know how to pass it in. Okay, and so the solution is to use a closure. Okay, so this is the actual solution. We'll call two functions, resolve Venus and resolve Mars. This is actually not a asynchronous function, it's just a standard function. So over here, we call a function resolve, and we're passing in the domain venus.csxedu. We call our Dns.Resolve function on our domain, and then when we finish, it's going to execute after resolution. So again, we'll pull up our architecture real fast. Okay, so this gets added to our task queue, and it'll go, which will get picked up by a worker thread. And then, so this function after resolution will be added to the event queue. Okay, so this function is now done. Resolve is finished, but our entire program is not finished, so we can't pull after resolution off of the event queue. Okay, so this stays inside the event queue for now. Our next function is resolve Mars. Okay, so, and again, we call function resolve on a domain. And important thing is over here is that when we call this resolve on Mars, it's a different domain than when we did on Venus. Okay, so this is just a standard function call. So this is a different domain than the domain that we used previously. It's a different instance of it. Okay, so the value of this domain is Mars. And again, we do the same process. Okay, so when this is finished, we'll have two events on our queue. And the order again is not guaranteed because the Mars one may finish a lot faster than the Venus one. Let's assume that Venus finishes first. And when Venus finishes first, it's going to execute its callback. We have the variable domain, which is enclosed under the entire function. So it still has a reference to the domain variable that was created when we called resolve of Venus. Okay, and again, it's very important to know that this is not the same variable that Mars is using. They share a name, but it's a different instance because it uses a function call over here. Okay, so for when we call this, Venus's value will be Venus and Mars's value will be Mars. Use omega. Okay, something that we did not visit. Okay, so these have flipped in this case. If we need to deal with n domains concurrently, we need to introduce a loop. So over here we have a loop that goes from 0 to domains.length and continuously calls resolve. When we called it twice, we were able to see that it created a separate closure for each one, which allows us to keep access to each of these domain variables. So that should persist, but there is a bit of sleight of hand in this scenario. And that's going to require us to look at a couple of examples, and we'll come right back to this. So inside of Java and most C languages, if we have a loop that looks like this, essentially equivalent to the following: int I outside of this loop, and then this for statement inside of it. And so with standard procedural code, this works fine, but it does not work well with asynchronous code. So these two pieces of code are equivalent, as we saw inside of the job example. Okay. So if we create this variable outside of this for loop, then every time we refer to it, it's referring to the same variable. Okay. This is in contrast to declaring a variable inside the for loop, where it will be a different instance every time because it's scoped to the block. So in both of these cases, if we run this program, okay, we'll see that it prints out the same value every time. In this case, 55555. Okay. Instead of what we expected, which would have been 0, 1, 2, 3, 4. Okay, because they share the same variable I, because I is defined outside of this for loop. So what we want the ability to declare I inside of this for loop. Okay, but this doesn't look syntactically correct because we're sort of using it over here. Okay, so the function, the construct let has that special behavior that we treat this declaration as if it were inside of this loop. Okay, and if we run this, you can see it prints out 0, 1, 2, 3, 4 as expected. Okay, because that's the sort of sleight of hand that when we use let, the declaration is as if it were inside of the for loop, not outside of it. If we run this application, each of these resolves, except for the two that are not domains. So there are two dummy ones that are not inside of here. Our next example has us going through multiple synchronous tasks. In this case, we're going to go through the same list of domains, but this time we're going to perform one after another instead of having them execute concurrently. One of the benefits of having it synchronous is that order is guaranteed. And if we're doing something like DNS requests, then in actuality, we can't make too many DNS requests at a time. So we do something like 6 or 7, that's not a big deal. But if we're looking at like hundreds or thousands of DNS requests, we won't be allowed to perform them concurrently. They'll time out before we get a response back. And that's because most DNS servers do have some rate limiting to prevent denial of service attacks. So if we're trying to sort of do hundreds of requests at a time, it's better to do it synchronously. Get one, sort of make a request for one, send it off to work, and then when we receive a response back, move on to the next one. And to do this, we typically utilize recursion. Okay, so we extend continuation passing style by counting how many requests are finished. Okay, so we have a counter over here that counts how many requests are finished. And as we get responses back, we're going to increase that counter. And then once that counter matches the number of requests that we made out, matches our domain counts, then we quit. But if we haven't reached that number yet, we send off another Dns.resolve. So essentially we bootstrap our application with a first Dns.resolve for the very first domain. In this case, count is 0. And then when that's complete, it calls the function after resolved. And inside of after resolved, if we are finished with all the domains, for instance, if there's one domain inside here, then we're finished, then we print. Otherwise, we get the next domain. We take the next domain because we increase count by 1, and we resolve that one. Okay, and so when that resolves, it'll add its information to the IP address array, And then again, it'll perform this check. And then eventually, as we add more and more and more data to the array, it'll fill up. And then we'll get to the last domain where it matches, and then it'll print out the IP addresses. Okay, so we can see that it prints out the IP addresses over here. And this will always print out the same order because it's synchronous. Okay, and again, we have two that are not real. We have earth, which is the third one, and then we have definitely not domain, which is the one before the last. Okay, so when we're doing something synchronously, the order is guaranteed. Our next scenario, we have a file domains01.txt that contains multiple domain names inside of it. We can very quickly look at it. Okay, so there are multiple domains over here. We want to read the contents of that file, and then only after the data has been read, we'll use Dns Resolve to convert each line into an IP address and then print them to console. Okay. So over here, in fact, we import our resolve function from our previous demos. It's exactly the same thing. Okay. And so this is what we're going to be using to resolve end domains. Okay. And again, we have our closure over here that closes over the variable domain. Okay. What's new is that is this code. Okay. So this time we're using the file system, specifically fs.read file, which is also asynchronous. And again, for DNS, it's pretty obvious why we need to do this asynchronously because it's using the network. For reading files, it's less obvious because typically reading files is pretty fast, but it's only fast to us as humans. To actual machines, it's fairly slow, depending on what you're using. And on certain hardwares, it can be incredibly slow if you're using something like a CD-ROM or a floppy disk. These types of hardware mediums are incredibly slow, or even magnetic tape, okay, compared to the solid-state drives that we have nowadays. So you don't know which hardware that you're using. Node.js doesn't know which hardware you're using. So because these applications have to work everywhere, then it's better to have these functions execute asynchronously. Before we can resolve the domains, we have to read the file first. Okay, it's impossible to start resolving domains without completing reading the file. Okay, so we are going to call fs.read file on the input file, which is inputs.domains.txt. Over here, we give it the encoding formats, which is how to interpret the data. Because this is text data, UTF-8 will be how we want it to interpret data. And then when it's finished, it's going to call the function after read. Okay. And inside after read, we split the data according to its new line characters, called the results domain. So this is just an array of domains similar to our previous examples at this point. And then we run our loop. Okay. And we're using this let statement over here again to ensure that the variable I, or domains of I in this case, is scoped to this loop. It gets declared as a new variable on each iteration of the loop. Resolve gets called n times, and because it has because it's closed on domain, it'll have a new variable domain each time. These will be done concurrently, and as each result comes in, thereafter resolution calls gets made. Okay, so let's run this. And in fact, let's keep this open over here so we can compare. Okay, so we can see that the order of these is not going to match what was actually called. So over here we can see Omega was first and Castle because we recently called these two. If I run this again, the order should be different. Okay, so now we have much more similar to how they're arranged. Okay, there is some preference to being sent out first, and that could affect the results. But the ordering is not guaranteed. Okay, no matter what, the ordering is not guaranteed. Even if you sort of had them cached, there could be other factors in play that changes the ordering of the response back if you're doing things concurrently. The next example has us starting a process concurrently. Okay, so we have an array of valid domains we want to convert to IP addresses. And then the final output should be a single string of IP addresses separated by new lines. So we want that string to be printed out. So the printing statement can only print after all the domains have resolved. But it's a single print statement. It's not 5 separate print statements. Okay, so we need to have some way to sort of collect the results of the resolve statements. And then once we're sure that the results have all arrived, then move on to the next stage. So we first declare our domain. So we have a bunch of domains over here. We have our library for DNS, and we have an array to store the results. Okay, so as we get the domains resolved from domain name to IP address, we're going to store them inside of here. And then we also have another count variable. Okay, so we're doing counting. So very commonly when you're doing these asynchronous tasks, most of the time the answer is just have a counter. Okay, so we're going to start off from I is 0, I is less than domains.length, and we're going to resolve each of these domains. So this is going to make a DNS request for each of these domains. Okay, so we're going to do this concurrently. Okay, so over here we have DNS.resolve, okay, which is going to call the function DNS.resolve to make a request. And when it's finished, it's going to call after resolution. So we can sort of like, we'll come back to this. Okay. So this function gets called as many times as there are domains. And then as it finishes, it moves on to the next one. So it's sort of scheduling this DNS. So resolve this domain, then resolve this domain, then resolve this domain. So all of these are sort of being added, and all of this is done concurrently. So we don't know which one will sort of resolve first because it depends on a lot of factors. Okay. As they finish their resolution, each of their individual domains is going to be added to the after resolution function, and these will be pushed onto the event queue. And over here is how we see that we can do our transition. So what happens is we take the record, okay, so the IP address, and we're going to push it into an array. IP address is subcount, okay. And then we're going to increase our count by 1. So moving on to the next. We're increasing our count by 1. So this will shift the next index over. And if our count, okay, so if our count matches domains.length, okay, so over here we have this if statement. This type of statement is going to be very useful if you're trying to go from concurrent to synchronous. Essentially what you're doing is you're counting the number of responses that you receive back. Okay. Notice that count over here is not scoped to this function. It's scoped outside of it. So it means that it's the same count variable. It's not the same domain variable every time. That's going to change every time. But the count variable is the same. So we have this sort of shared variable. And so we're going to increase it until it reaches domains.length. When it increases when it reaches domains.length, that means that that we've read everything. So we don't even know the order that it'll come back in. Maybe it'll be this one first, then this one, then this one, then this one. We don't really know the order. So we can't say something like when the last one comes back, because it might not be this one. This one might resolve right away if we recently visited it. Okay, so we don't know the order in which they resolve in. So all we can do is count how many have resolved back. And once we get, in this case, 1, 2, 3, 4, 5, once we get 5 results back, then we know everything's been resolved. Okay. So what's actually going to happen is that when this code runs, this function is going to run 5 times in total. Okay. Similar to when we did our concurrent examples. Okay, because there's 5 DNS resolves, which means that there's going to be 5 calls to after resolution. Okay, but what's key here is that 4 of these calls are not going to execute this statement. They're going to increase count, finish, and then move on to the next one. The very last one that executes will be the only one that executes this statement, because that's the only time when count matches domains.length. It's also important that this function as a whole, there's no sort of race conditions here. This function as a whole must complete before the stack is considered empty, and I can pull off the next after resolution function. My mistake, this function over here. This function must be completed entirely before the next after resolution call gets pulled from the event queue onto the stack. So this check and this count plus plus always occurs. Okay, we can't stop in the middle of here to pull off another task. So we don't have those race condition problems. And then when the count finally reaches domains.length, then we perform the next task, which in this case is to take all the IP addresses. I think in this case they're doubly nested arrays, and the flat function essentially just makes it a single array. Okay, so it's not an array inside of an array. And then we use the join statement to combine them with new line characters, and we send it to next task for printing. So let's try Babbage. Let's see, right, so 181 moved to the top, and 0.20 would be Babbage. That would be moved to the very bottom because it's a new address. Okay, so the order is not guaranteed in this case, but once we get them all, it prints out the results. So order is not guaranteed in this case, but sometimes you do want to guarantee the order. The way to preserve order is to reserve space for each individual result. And in addition, you not only pass the domain into the closure, but also the index. So you preserve both the domain name and the index. Okay, so over here to reserve the slots, we have a function array. And what this function does is if you give it a number, it will create an array with that many empty slots. So in this case, I'm going to create an array with domains.length number of slots. So that's going to create an empty array, in this case with 5 empty slots. And then we're going to loop through our domains array and resolve domains of I, and we're also going to pass I. That way we can preserve the index so that when we say, okay, we finish resolving, let's say, venus.csxunit.edu, when we finish resolving this domain, then we know which index is it's referring to. It's referring to index 0. Or if we're talking about cs.qc.uni.edu, we know that that's index 2. Okay, so you don't have to, you're not limited to preserving a single variable when you use closures. You can preserve as many as you want. So over here, we call our Dns.Resolve function, domain and after resolution. And then once after resolution happens, we have our records variable, which contains the IP address information. And this is the key to preserving our information. Okay, so because we preserve the index variable, then we can go to IP addresses, which is a array with a bunch of empty slots. So whichever one finished first, let's say that's the very last one finished first, the index 4. Okay, so then we're going to go IP addresses of 4, okay, because we preserved this index, is equal to records. So it just places it into the empty slots. And as they come in, because we have this index, as this one finishes, this one will go into 2, this one will go into 0, this one will go into 1, because we preserve that index variable for each of these. And so when we print it out in this case, these will always have the same order. And that's in contrast to before, where we printed them out in the order that they came back in. Okay, so in this case, this is always going to print them out in the same order. Okay, and so let's see. All right, so over here, this statement over here is just always printing out the results as they work through it, so that we can sort of see the order that these things are being populated in as they progress. So in this case, the first domain to complete was the vns.cs.qc.edu, and that one finished, and then we had 4 more empty arrays, and then the next one to complete was Mars. Okay, so it's 1, 2, and then 3 empty ones, and then 1, 2, 3. So these completed in the order that they came in. Okay, but I'm going to change this a bit to a domain that I haven't visited recently. Okay, and so if I run this now, we'll see that the one that came back first was not the first one, in this case nyu.edu. This was not the first one to come back, but Mars was the first one to come back. So that's placed over here in its slots. Then cs.qc.edu, then qc.qc.edu, then quni.edu, and then finally we have the nyu.edu domain, which comes back last. But because I reserved the slot for it, it goes into its 0th index slot. And the results print out always the same. So if I run this again, now that we have that one cached as well, then it'll most likely appear first. Again, it's not 100% guaranteed. There could be just bad timing issues that can affect this result. But the final output will always be the same in this case. Okay, it's just the order of these messages is showing it will appear somewhat at random, because we don't really have any guarantee of when they'll come back. All right, so the next example has us compressing data. Compression is the process of taking data and re-encoding it such that the resulting output has the same information but in fewer total bytes. Because this process is CPU intensive and can take substantial amounts of time, its API was designed to be asynchronous inside of Node.js. Okay, so we call the function zlib.deflate. We pass it the content that we want to compress. And then when we finish, it'll call the callback after compress. And after compress has 2 parameters that it gives us. It gives us an error if there was some error in the process. And then we get a buffer type variable if it was successful. And the buffer type is a sort of storage for binary data. Okay, so we can't read this information directly, but we can write it to some file. Okay, so that's what we do over here. We take that binary data and we write it to a file content.deflated. Okay, and then after we write that, so that function takes a file name, a data to write, and again a callbacks. Okay, so what do you want me to do after you finish writing that function, that file? So in this case, when that file is finished writing, I want a message file written to location printed out. Original size will be this content.length, and then the new size will be buffer.length, just to show that it was compressed. Okay, so let's run this first. Okay, so this created a new file, content.deflated. The file size of that file, if I just look at it, is 570 bytes, which it says it over here. Okay, the original size is 1232, which is just the number of characters inside of the string. Okay, so it's a long piece of text. So we can see that this piece of text was compressed. Okay, and then in the next example, we will decompress it. Okay, but before we do that, we have another test for you to try out. So these two functions are sort of nested inside of each other. So we want to call fs.write file after we call zlib.deflate. So we need to put this sort of inside of the callback, because we only want to write the file after we are sure that the compression is finished. Okay, so we need to put this function call inside of here. And this is going to be, we keep on sort of doing this. Let's say that we wanted to do something else after we wrote the file, we want to do another asynchronous task. We can sort of see that we can sort of bubble up in this sort of complexity where we have a function inside of a function inside of a function. And this can get really out of hand if you're, let's say, writing 5 files or alternating between tasks. Okay, so your task in this case is to modularize this code a bit. So this callback, I want you to move outside of here somehow. Okay, something like this. Okay, and you're going to see right away that you're going to have a bit of difficulty. Okay, the key thing that's going to be problematic is that you no longer have access to this buffer variable. Okay, so how can you import this buffer variable into this function? Okay, because buffer variable is scoped to after compress, and if you're not inside of after compress, what techniques can you use to move it out of? So again, it's really important for you to try this. You don't actually have to solve it on your first attempt, so I'll give you the answer afterwards. But it's important for you to try it to understand what problems that you're trying to solve, that we're trying to solve. Okay, so we're going to take a couple of minutes and we'll go over the answer afterwards. Okay, so the solution here is to use what we call a wrapper function. In this case, I use an arrow function for succinctness, but you can just use a standard function as well. Okay, over here is the major change. Okay, so what I had initially was that I had after write over here. So when you finish, call after write. And the problem with that is that we needed some way to pass this buffer variable into after write, and the only sort of actual variables that it had initially is just an error. Okay, it only has error. Okay, there is no secondary variable. So what the solution does is it takes this function, okay, which only has an error. Okay, in fact, we can look up the the FS library to very quickly confirm that. Let's go to file system, fs.write file. Okay. So the callback to this only gives us an error. It doesn't give us anything else besides an error. Okay. So it only gives us one parameter. And so we're going to take that one parameter and we're going to write a new function. Okay. And this function, all it's going to do is call after write. Okay. We're writing a new after write function that has two parameters. It has a error and a new size. Okay, so we're forwarding this error variable and we're adding a new variable buffer.length. And so in this case, we are forwarding, right? This wrapper function is sort of forwarding data to the next function. We're forwarding it to after write. So even though the original function only gave us a single argument error, we took that function, that callback, and we called a new function that has two parameters. Okay, so that's how we can pass. And this technique is used very often to pass variables forward, where you want to use a variable later on that you have right now. So you write a wrapper function and you pass it forward. Okay. So we catch those variables error and new size. We take care of the error if there is any, and then we can print out the new size of the variable. Okay, so let's run this. And again, we get the same output. So this time we're running the function in reverse. We're running decompressing data using the inflate function. And this uses the zlib.inflate. So first we're reading a file. Okay. When you're reading a binary data file, okay, you're going to use encoding null. Okay, so we know that this data is binary. It's just a bunch of garbage characters. If I try to open this file in a text editor, this is what I'll sort of see. It's just a bunch of garbage characters. Okay, so when you have data like that, it's encoded using null. Okay, so we're going to read that file, and then after we finish reading it, we will call a function after read, which will use zlib.inflate. So after we move that data into memory, we call zlib.inflate on it to decompress it. And once it's finished decompressing, okay, we'll have a buffer. Okay, when you decompress data, you get a buffer, but you can convert that buffer into a string, and it'll typically ask you which string encoding format you want to use. And in our case, we'll use UTF-8 because that was what the string originally was. And instead of printing out the massive blob of text, we'll just print out the compressed size, which is the original data that we read .length, and the decompressed size, which will be buffer.length. Okay, so let's run this. Let's see. Okay, so in fact, over here, I think we do print the data as well. Let's see. Oh, we do it. Okay, so over here we do console.log buff.toString. Okay, so that just prints out all the data as well. And then afterwards, we print out the compressed size, which was 553, and our decompressed size 1005. And what I'm going to do, just to make sure that I can prove that this works, is I'm going to take the outputs from the 13th example, and I'm going to decompress it using our new one. So I'm going to replace this file. Okay. And then I'm going to run it again, and we'll see that I get 570 and 1232, as well as the original message that we saw previously. So this does work. Okay, so we're able to compress and decompress files that such in a way that we do not lose data. We preserve all the information. Okay, so again, take a couple of minutes to try to decouple this function now that you've seen it once. In a second, I will come back and give you the solution to that. Okay, so to decouple this function, again, we use the same technique. When we do, after we finish reading the file, we have some data, and the zlib.inflate function, which we can go to inside of the library. As you work with the Node.js API, you're going to find yourself constantly going back to the specifications to see what are the arguments that we're going to use, and what callbacks and what are the parameters inside those callbacks giving us. Okay. So after read, reading a file gives us two parameters inside a callback: error and data. And when we do zlib.inflate, this will give us back a callback. And let's see, there's not a lot of information over here. Sometimes it's a bit sparse. Okay, so we might have to go into the actual code to figure it out. But just take my word for it that this function will give you two variables, error and buffer. Okay. And error just represents any error that you might have had, and buffer is going to be the inflated data. Okay, because it doesn't know whether this data is a string or another binary format. So you can sort of double compress files if you wanted to. Okay. So because of that, this is going to be a buffer and not a string. Okay, so what we do is we pass in these two arguments. Okay, so this time we have two arguments, but what we actually do need inside of here is we want to be able to pass in the original size. Okay, so that's going to be sort of this data.length. Okay, and because inside of this, after decompress, we no longer have access to the data variable, we need to have some way to preserve it. Okay, so that's what this wrapper function does. It takes these two variables, error and buff, that zlib.inflate gives us, and it calls a function after decompress where it passes in these two original variables, but then we augment a third variable, data.length, to it. So that our function now has the two that were supplied by the API plus our own third variable, compress size, which allows us to print out these two values. Okay, so that's how you sort of decouple this function. So in this course, you will not be allowed to use, in this course, you're not allowed to use the set timeout function. I can use it, but you are not allowed to use it. But if you're using it while you're trying to learn asynchronous tasks, you can misuse it to create what we call artificial delays. Okay, so one of the very sort of common issues that I would see in sort of students' exams and homework in the past was that code like this would be written, where, let's say, the thought process of the student who's sort of first doing asynchronous programming In this case, they want to write the contents of a file and then print a message, finish reading file so-and-so. Okay. This one I think can just run directly. There's no DNS requests over here. Okay. So what's happening is, in fact, I think it's file 1. So let's fix that and run. Okay. So whoever's running this code is going to encounter this problem, okay, where they include the FS library, they create a variable file contents, and then they load the file index file01 into memory, in which case they'll move the contents into file contents, and then they'll try to print it out. Now, if we go back to the architecture, we'll sort of see, we can see right away why this doesn't really work. Okay. And that's, this is a asynchronous call. Okay. fs.read file is a asynchronous call. Okay. So this task gets, so it doesn't actually, because we're going to disk, it goes to IO polling and not a worker thread. But it's the same idea. When this finishes, okay, so let's say that this takes let's assume that it finishes immediately. Okay, we're gonna give the student who made the mistake the benefit of the doubt that it finishes the exact moment that it goes in. When it finishes, the results will go into the event queue. Okay, so it moves into the event queue, and it doesn't move from the event queue into the stack until the existing program is finished. So this will always print out first, in which case it will print out finish reading file. And then in this case, it's trying to get the file contents.length. This question mark over here is if this variable doesn't exist, then this prevents a null pointer reference error, null reference error. So if this thing doesn't exist, then it will ignore the rest of this. It'll just print out undefined. But if this does exist, then it'll print out that length for it. Okay, it's just used to prevent null pointer errors. Okay, but this will always print, and because this variable file contents because this has not triggered yet, it's still stuck on the event queue, then it's going to print out undefined, and then this will happen. But at that point, there's no more print statements. So very common mistake that sometimes gets done is that to avoid this problem, okay, so to sort of sidestep this issue, students would sort of set a timer. They'll be like, they'll think that this is finishing way too fast. I have a race condition. This is they'll think that this is running way too slow. Okay, but in reality, even if it finished immediately, you would still get that problem. Okay, so they'll think it's running. I'll just wait 1 second, and then it'll work. Okay, so what happens in this case is that you have two processes. Okay, fs.read file and this set timeout. One goes onto the IO polling and one goes onto the worker thread. Okay, and there's no guarantee which one finishes first, but most likely if you're reading a small enough file, then this one finishes first and it gets moved to the event queue, because this one is literally just waiting 1 second, and then 1 second later the worker thread is finished, it'll move that over here. So at that point, because you waited that 1 second, this process is more likely to be in front of this one. Okay, but again, it's not guaranteed. If you have a very slow disk, then this one still might be in front. Okay, so this actually introduces race conditions. You don't know which one finishes first. Okay, you're not guaranteed it. So in this case, if this one finishes first, then it will print out, it'll assign the variable file contents to data to file contents, and then this second task will print out the correct output. Okay, so in fact, if I run this, it should work. Okay, so it prints out 11, which is just the hello world message. Now, there are two problems with this. First of all, we have race conditions. Okay, before we did not have race conditions. In fact, with this original statement, we did not have race conditions. It would always run this before it ran this. Now we actually do have race conditions because we don't know which one will finish first. Okay, so you might say that waiting 1 second is sufficient, but it's only sufficient for this really tiny file. So over here, I have a script that generates a much larger file. This will generate a file that file 02, which will be 512 megabytes in size. And if you want to increase it further, let's say you're using an SSD or something, I'm not using an SSD over here, then you can just increase this number from 27 to 28 or 29. 29 will create 2 gigabytes. 30 will create 4 gigabyte size files. But right, the only limit is your specific disk, your own disk capacity. So I'm going to run this. It's going to create a massive file. It's going to take a while because it's writing data. And then over here, I have a file that is roughly 512 megabytes in size. Okay, so I'm going to go back to our mistake file, and I'm going to change this from file 01 to file 02. Okay, so I'm going to load this into memory, and then when it's finished, I'm going to print out the size. Okay, and remember before it worked because 1 second was enough to read a file that was 11 bytes in size. But if I give it a 512 megabyte file, we're going to see that it's not enough time. Okay, now the other problem is that now let's say that I have a very small file. Okay, then that file is going to take 1 second to read because we don't know how large this file can be. We're always going to wait 1 second to finish reading that file. And that might not be a big deal over here, but it becomes a big problem when you have to do this multiple times. So you might have to read this file and then perform this network task and then perform this network task and then write this file. So that's 4 of them already. You're introducing a 4-second delay to your program. And if you have to do anything multiple times, let's say that you have to read 5, 10, 100 files synchronously, then you might have a 100 factor towards this 1 second delay because it has to wait that amount of time to actually read the file. And then again, if the file is even larger than that, that might not be enough time. You might need 2 seconds to read a file, in which case your program breaks entirely. Okay, so that's why I don't let students use set timeouts. They abuse it to sort of create artificial delays. And it's not on purpose. It's just that they don't understand asynchronous programming initially. And I found that in the past, getting rid of this function from their sort of toolkit solve the problem, and then you can add it back later on when you're more proficient. Okay, so for this course, you won't need to use set timeout at all. I won't give you any questions where you need it. And then outside of this course, you typically use set timeout when you need to simulate some type of time passing. If you're using it to create artificial delays, such that another function finishes first, you're using it wrong, and you are also introducing race conditions. And at this point, you should be able to tackle the assessment problems that are available to you. So that's going to be it for this lecture. I hope it was enjoyable.